Hello everybody, welcome back to another lecture. Today is the lecture number 6. We're going to talk today about Boolean Algebra. And so, as we said before, as we keep saying, modern digital systems use 0 and 1, so false, true and false, to describe values, and Boolean equation to describe the behavior of the circuits and systems that we want to develop. And as we use algebra to simplify mathematical equations, we're gonna use Boolean algebra to simplify Boolean equations. And those rules of Boolean algebra are much like those of the ordinary algebra, but in some cases are actually even simpler because we are only dealing with two possible values, the 0 and 1. And so, first of all, Boolean algebra is based on a set of axioms that we assume that are correct. We cannot prove the axioms, we just state that, and we use those axioms to prove all the theorems of the Boolean algebra. So those are sets of definitions that we have to use in order to have those equations and those simplifications that we want proven and working. So first of all, there's two main values: 0 that we're gonna represent, that's gonna represent false, and 1 that's gonna represent true. If a variable is 0, it's false or it's 0, it cannot be 1. It's only one possible value for that variable, and if it's 1, that variable cannot be 0. And the complement of 0 is 1, and the complement of 1 is 0. So, and that defines our first operation that's not or complement. Sometimes you see in the literature. And we're gonna define two other operations, that and this is the definition, and we can say that this operation is only true if both variables are true. It's one way of defining this variable. So if 0 and 0 is 0, 0 and 1 is 0, 1 and 0 is 0, and 1 and 1 is 1. And another operation that we're going to define here is the OR operation. So another way to define this operation is if one variable or the other, A or B, are true, my output, my operation is true. So 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, and 1 or 1 is 1. The textbooks has a really good summary of that, and we're gonna see through this class that we have the duality of Boolean algebra. We have most of our definitions. We have a definition for and we have a definition for or. So in the same way, so we define 0, and if a variable is 0, it cannot be 1, and if a variable is 1, it cannot be 0 again. So complement of 0 is 1, complement of 1 is 0. And so in the the definitions of 0 and so we have definition for 0 and 0, and we have definitions 1 or 1. And again, so we always have this duality. So we have the definitions for and we have the theorems for and we're gonna have the different definitions and the theorems for or. So let's start with some theorems and definitions that we're gonna use through how to simplify these equations in the future. So those what I'm gonna show here are single variable Boolean algebra theorems. For example, A and, so this is the operator for and. Sometimes we're gonna use them together, just like A and the two variables together means and as well. So A or any variable and 1, it's equal to that variable to A. For example, here in the circuit we're gonna define this way. So A and 1 it's gonna be A. So if it's 0 here, it's gonna be 0 here. If it's 1 here, it's gonna be 1 here. And we can see in the truth table that A is 0, can be 0 or 1, and 1 is just 1 and 1. So when we have the operation A and 1, 0 and 1 is 0, 1 and 1 is 1. So this, so the output of this function here is the same as the first variable that we have, A. So the identity for OR. So A or 0, it's equal to A as well. So in the same way, we have the digital circuit here for OR, and if this guy is 0, it doesn't matter what I have here, it's gonna be the same output here. So A or 0, 0 or 0 is 0, 1 or 0 is 1. So you can see that this output here is the same as this one here. Annihilator for AND. So if you have A or any variable and 0, the output is 0 in any case. So you can see the digital circuit will be like 0 here, and any variable that goes here, the output is going to be 0. So 0 and 0 is 0, 1 and 0, it's 0. And the annihilator for OR, it's 1. So if I have any variable here, anything here or 1, it's going to be 1. So 0 or 1 is 1, 1 or 1 is 1. So this output here is the same as 1 all the time. So this is the single variable Boolean theorems. We have the idempotence, sorry about that, for and OR. So if I have A and A, it's equal to A. So if I have 0 and 0 is 0, 1 and 1 is 1. And if I also have A or A, it's equal to A. So if we have the same variable here for the operation AND, the output is the same. And here the same with the OR. So 0 or 0 is 0, 1 or 1 is 1. And we also have the complement. So if I have A and complement of A, it's equal to 0. So 0 and 1 is 0, 1 and 0 is 0. So it's always 0. If I have any variable, anything here, and the complement of that thing, it's going to be 0. In the complement of OR, it's 1. So if I have 0 or 1, it's 1. 1 or 0 is 1. So it's always 1 here, independent of what I have here. Independently of what we have here. So A or complement of that thing, the A, it's equal to 1. Also, following this, still in single variables Boolean algebra, the involution or the double knot can cancel each other. So you have the A, for example, and you have a double negation or a double complement or a double knot. It's equal to the variable, to the same variable. So the knots cancel each other, the double negation cancel each other. Do not mistake with this operation here, where I have the A, for example, it's complemented, and over the operation I have a complement. So that's different from canceling these two ORs, and we don't have A or B after this operation. We're gonna see that we have we have the De Morgan theorem, sorry, that explains what happened here. So actually, this is gonna change the operation that's happening here. Instead of OR, we're gonna be an AND, but that's in a couple of minutes. So multivariable. So when we have more than one variable, if we have A and B, it's the same as saying that we have B and A. Doesn't matter the order here. That's commutativity. So the commutativity for OR is the same. So if you have A or B, it's the same that we have B or A. That means also that in our circuits, doesn't matter the order of the inputs that we have. So that simplifies a little bit our development. The associativity for AND, so we have A and B and C. It's the same of saying that the A and B and C. So it doesn't matter the order of the parentheses here. So, and that's kind of helpful when you're simplified as well, when you're simplifying equations. You can change the variables orders, and that doesn't affect the end result. And we also have the associativity for or. It's the same, so R, A, or B, because we know that in some so we have sometimes some operations we cannot have the associativity on regular algebra, right? So A or B or C is the same as saying that A or B or C. So it's the parentheses here show that doesn't matter which one you do first, it's going to be the same. So let's move on into something a little bit more interesting for our simplifications. The distributivity of AND over OR. So if I have A and B or C, so this operation, it has you have to do it first. So it's not like A, B, and after that or C, A and B after that, it's B or C and A. And that's the same as saying that's A and B or A and C. So you can distribute the A over the OR here, the AND operation over the OR. Let's check this with truth table. So this is the exhaustion proof. So we have A, B, and C, and B or A. So B or A are, so if we look here, 0, so 0, 0, 0, 0, 1 is 1, 1, 0 is 1, 1 and 1 is 1, 0 and 0 is 0, 1, 0 and 1, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. So that's B or C. And when we do the rest of the operation, A and B or C, we're going to check here, right? So 0 and 0 is 0, 0 and 1 is 0, 0 and 1 is 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 1 and 1 is 1, 1 and 1 again, it's 1. So this is A and B or C. And if we look into this side of the equation, we have A and B, so A and B, 0, 0, 0, 0, 0, 0, 0, 1 and 1, right? And A and C, so A and C is 0, 0 and 1 is 0, 0 and 0, 0, 0 and 1 is 0, 1 and 0 is 0, 1 and 1 is 1, 1 and 0 is 0, 1 and 1 is 1. So, and when we are those two together, so A, B, or B and C, A and B or B, A and C, these two, we're gonna see that 0 and 0, 0 and 0, oh, 0 or 0, 0 or 0, 0 or 0, 0 or 0, everything is 0 up to here, 0 or 0 is 0, 0 or 1 is 1, 1 or 0 is 1, 1 or 1 is 1. So we can see that this equation here, this behavior is the same that we have here. So by exhaustion, so you check all the possibilities, you can see that A and B or C is the same as A and B or A and C. So this is the distributivity of AND over OR. And we have the same with OR. So A or B and C is the same as A or B and A or C. I'm not gonna go again of this. So we have B and C here. You can check that here. And A or B and C. So if you check A against this one, A or B and C, we have this. And from the other side of the equation, we have A or B is this guy here, A or C. And if we end those guys together, we have this output that's the same as this other side of the equation. So you can see by exhaustion again that we have is the same behavior as having A or B and C is the same that we have A or B and A or C. And keep in mind that it's from here to here and this way. So if you are sometimes in Boolean algebra, you expand a little bit. So you your equation is a little longer and has more inputs, but in the end you can reduce that because we're going to combine with other members of the equation, and that's gonna be simpler. So sometimes you come from here to this side, not the opposite, to reduce. So yeah, so more simplification. We have the covering. In some places you can see as absorption of and or. So A and A or B is equal to A. So that's really useful. You can see that we are removing two operations and one input. So that's really useful. And again, we have the duality here. So we have A or A and B is equal to A as well. And another, that's the combining. It's kind of an absorption as well. I think I've seen this as called an absorption. And we have A and B, or A or B. So we have the complement of the second variable here, and that eliminates, and you only have A. So A and B, or A and complement of B, it's equal to A. And we have the same version for OR. So we have A or B, and A or complement of B is equal to A as well. So that really helps you simplify, and usually, actually, because of the simplicity of the Boolean algebra and the Boolean equations, and that mostly because you have only two variables, and that's possible to have those simplified. So I was just gonna show one proof of absorption. That's this first one here. Actually, sorry, the second one here, where I have A or A and B, and it's equal to A. So if we take this equation here, A or A and B equals to A. So okay, that's gonna, if you apply the distributive law, where I have A and something or other thing, and we can you can remember that A and 1 is equal to A. So if you go back here, so A and 1 is equal to A. So every variable that we have here, everything in Boolean algebra always have one here following, ending, let's say, because it doesn't matter, like you always have this one here, even if it's hiding. It's the same that you have when you have a number and it's always power of 1. So yeah, it's the same thing in regular algebra, right? So going back here, we have A, and by the distributive law that we've seen here, so A and, no, sorry, it's this one here. So A and B or C is the same that's having, no, like, I forgot, sorry. Yeah, so yeah, exactly. So we have A and 1 or B. So that's the distributive law when you apply this, because we have a 1 here. So if you go back to the you can see this one going this way. It's easier, I think. So A and 1 and or A and B. So this is the opposite of the distributive law. And so it's, as a result, we have A and 1 or B. And this 1 or B, it's equal to 1. If you go back here, anything that's or 1, it's equal to 1. So it's the annihilator for or. So A or anything or 1, it's equal to 1. So if you go back here, so yeah, all this member here, it's equal to 1. And again, A or anything and 1, it's equal to A. And if you go to the truth table, we have like A here, and we have B, and we have A and B. So A and B is 0 and 0 is 0, A is 0 and 1 is 0, 1 and 0 is 0, 1 and 1 it's 1. And if we apply the OR, so A or A and B, so A or this is 0 0, 0 or 0 is 0, 0 or 0 is 0, 1 or 0 is 1, and 1 or 1 is 1. And you can see that this output of this equation here is the same as A. So also by exhaustion, you can prove that the A or A and B is equal to A, because it's the same output that we have here. More simplification. So we also have the consensus. So this one is a little harder to see, but when you have three variables and you have a complement of one of them with the others, usually you can see that the third element of this equation, B and C, because they are already represented here, you don't need to have this guy here. So A and B, or complement of A and C, or B and C, it's equal to A and B, or complement of A and C. So this guy here doesn't have to take in account, so you remove it. And for the duality, so you have for the OR as well, A or B and complement of A or C and B or C, it's equal to removing B or C, because you already have them right here. This one is a little harder to prove, but again, that's one rule. I'm gonna talk about the examples in a bit. So yeah, that's the consensus. More simplification, we have the De Morgan's law. So that's a really useful law, actually, because that's gonna provide us with techniques to move from one gate to another. And basically is if I have an operation that's ORed, that's negated, sorry, it's not ORed, that's negated, or is the complement of an operation, is the same as saying that I have the other operation with the components negated. So if I have an AND, so A and B complemented, A and B complemented, it's the same as having A complemented or B complemented. So that's not the same as removing, for example, if we go back, when we have two, we have the A negated or in complemented of the operation. The operation complemented means that after I'm doing this operation, the AND, it's the complement of that. And that's the same as saying that the other operation, in this case OR, with the components negated or complemented. And the same with OR. So if I have the operation OR complemented, is the same of having the operation AND with the components or with the variables complemented. So yeah, so in digital components, like in electronic components, the NAND port would be the same as an OR port with both inputs complemented or negated. Remember that this small circle here means that NOT gate. The same is this way, but usually this means a port, an actual port that you can use, and this means OR, but with two NOT gates here. Usually that's what this means. You don't actually usually have this port here. You have an OR port with two NOT gates. And in this case, you actually have this port here available in some systems. And it's the same with the NOR. So you have the NOR gate here. It's the same as having the AND gate with two NOT gates on the inputs. And this is really helpful because you can move between the ports and have a that's really useful. And there's other aspects of NAND gates and NOR gates that we're gonna investigate in the future as well. So yeah, so now we know how to simplify our operations, our equations. But now we are going to learn how to write a Boolean equation from any logic function that you have the truth table. So you have the truth table here. So this is the truth table. You have A and B, and you have the behavior that you want. In this case, is the OR, and we're gonna learn how to extract that to an equation that works with any truth table. And basically, we are gonna do the sum of products, and that's a Boolean expression that contains and, or, and not operators, contain all the variables ended, and the products or the ended or the end components are ORed together. So let's see how that works. And any Boolean function can be described using a sum of products expression. So, and again, that's not a minimal form. So you can actually, after having this version from the truth table, it's really usually you have to simplify that equation. That's not going to be the minimal form, but it's one way that you have an equation from any truth table. So what we're going to do, we're going to just extract from this table when this equation is true. So this function is true when I have complement of A and B, A or complement or A and complement of B, or A and B. So every time that my equation is true, I'm going to extract the components here following if it's complemented or not. So for this one, I have complement of A and B, so 0 and 1. So when it's 0 and 1, it's true. I also have A and complement of B. When this happens, it's true. And when this happens also, it's true. So and when I have A and B, and I know that A and B are it's true, or A and complement of B is true, and A and B is true. So this will define my function. And as you can see here, so complement of A and B, or A and complement of B, or A and B. And you can write your circuit based on that. We know that the OR, we have the OR gate. So we could just have A connected here and B connected here, but this is a generic form of having the OR equation. And as you may expect, like this guys will be always the same, right? So why can I define, okay, I have this, the first one is 0, the second one, I'm just gonna use the second one, this third one, and the second one, the third one, and the fourth one, and that's how you define those equations. You can define those equations using Minterms. That's basically so I'm just gonna use the Minterms, or the terms of sum of products where my function is true. So this truth table can be specified by listing the Minterms that are true. And the definition of Minterms is equivalent of the sum of products, because I know what this Minterm tree represents. So it's always the same. So these three guys are complement of A and B and C. The second one will be complement of A, complement of B and C, and it's based on the inputs that I have to provide here to have this output. For example, this function f here has Minterms 3, 5, 6, and 7. How can I write this? Sum, because it's a sum of products. Addition of products of Minterms 3, Minterms 5, Minterms 6, and Minterm 7, or just sum 3, 5, 6, and 7. So this is a really compact way of describing this function. When you expand that, you have to, okay, I'm using the Minterm 3, so is this guy, complement of A, B, and C, or Minterm 5, sorry, A, complement of B, complement of C, or C, 6, that's A, B, complement of C, or Minterm 7, that's A, B, and C. And as always in Boolean algebra, we also have the product of sums. So this is sum of products. So we're gonna also have a representation of product of sums. In this case, we're gonna use the complement of the output when our function is false. So you can see that's the opposite what we just did. So in this case, we're gonna use, for example, to represent and, it's A or B, not the complement of A or B, it's A or B where my function is false. So A or B and A or complement of B, because in this case it's one, or and, sorry, complement of A or B. So the function is the opposite, so it's the product of sums. And we also need, we can, so we are gonna use everywhere my function is false. So, and in this case we don't use the term Minterms, use the term Maxterms. So in the same way, we're gonna use the components here. So this my function on the Maxterm 1, I'm gonna use it to represent, and my function on Maxterm 2 I'm gonna use to represent. And remember, it's not like complement, because here is 0 and 1. It's not the complement of A and B. It's A and complement of B. It's the opposite of what you see here. And that's gonna, so it's the equivalent to a product of sums. Oh, sorry. The Maxterms is it's the list of Maxterms is the equivalent to a product of sums. So in this case, this function here has the Maxterms M1 and M2, and we use the product symbol here. I forgot this name. Like it's the product of Maxterm 1 and Maxterm 2. So product of 1 and 2, instead of having the sum of the Minterms, we are going to have the product of the Minterms. And remember, the Maxterms are OR together, so it's a addition, it's plus. So that's two ways of representing equations. I'm gonna that's what I was gonna mention before. So I'm gonna do an extra lecture about this one, because I didn't want this one to be really long, so it's already like half an hour. So I'm gonna upload an extra lecture of simplification examples. So I'm gonna have a camera just writing some examples and explaining how to simplify them. That's gonna be an extra lecture. I think that's really important. Next class we're gonna have K-maps. It's a really useful way of simplifying equations as well, and simplification of Boolean expressions. And that's it for today. Thank you.